In this video, we will be exploring the white light tool on Predictive Science's new MHDweb 2.0. This tutorial is part 7 of a 12-part series that is designed to guide users through this website's data visualization tools. If you have not done so already, it is recommended that you review part 1 of this series, which covers in greater detail this website's architecture, general visualization workflow, and the mass run database. That being said, to get started with white light visualizations, navigate to the MHDweb landing page. Once again, that is predpsi.com/MHDweb2 and click on the white light button right here. For this demonstration, I will be using a steady state run, particularly the Carrington Rotation 2290 Thermo 2 run right here. Within the white light page, you are presented with two distinct approaches for generating white light plots. The first, which is the default approach, is by toggling the custom view off and selecting an instrument from this drop-down menu here. We have 7 distinct white light imagers that are represented here, including Parker Solar Probe with its WSPR 1 and WSPR 2 right here, as well as the newly launched Punch mission with its Near Field Imager, or NFI, and its Wide Field Imager, WFI. We've also included a general purpose Earth view, which is not necessarily tied to any particular observatory. So the instruments that are provided in this drop-down menu have predefined fields of view and occulters specified by the instruments themselves. The spacecraft Ephemeris is queried using Jet Propulsion Laboratory's Horizons API at the time of interest that is selected in the simulation widget. One thing to keep in mind, as with other comparison tools, is the respective time frame for these missions. So certain mass runs will not be compatible with an instrument selection simply because the run time range does not intersect with the mission time range. Also, you can find further documentation on Ephemeris availability at the JPL Horizons link that I will provide in the video description below. By toggling the Style Customization button, you have access to changing certain aesthetic elements of the plot itself. A default color map corresponding to the instrument in question is selected as you switch between instruments. However, this can also be changed by clicking on the color palette button here. You'll see this pop up in Plot 2D, Spacecraft Mapping, etc. The data widget also allows you to perform certain transformations on the data itself, namely radially filtering by a certain predefined vignette function here. You can also radially scale the data by a certain power, or you can take the logarithmic transformation. And lastly, you can also show the inner and outer boundaries of the run's radial domain with these toggles here, as well as the rotation and orientation, which is defined by the P angle, and that will be displayed on the plot itself in the lower left-hand corner here. And speaking of domain limits, a certain validation error that pops up is the incorrect domain for current view, which you will see over in the simulation widget. And this error is indicating that the field of view contains no values that fall within the current run domain. It's sometimes not immediately apparent if a field of view falls within the run domain, considering that the degrees of line of sight is a function of radial distance. So the quickest way to resolve this issue is by selecting another domain within the simulation widget. So currently my field of view, which is a little bit over 1 degree symmetrically, falls within the coronal domain, but if I was to select the heliospheric run, you would see that validation error that I mentioned pop up right there. So I'm going to go ahead and select the coronal domain again. So just to explore some of these options, so currently I have Earth view selected. But for Carrington Rotation 2290, if I wanted to select what does WSPR 1 look like during this time range, see that right here. And so this is what Parker is seeing, or a simulated version of what Parker is seeing at October 30th, 2024. And that corresponds to the time of interest. Since I have no time of interest selected, it's simply taking the midpoint of the run time range. Similarly, I could take a look at METIS. You'll see that color palette change to correspond to this white light image. We have that, and we can do one more. Let's take a look at the punches NFI. And you can see the green circle here corresponds to the model inner boundary, and the red circle here corresponds to the model outer boundary. So 1 solar radii and 30 solar radii, respectively. The second approach for constructing a white light plot is by toggling on the custom view switch. So this feature enables a more advanced set of specifications for plotting a white light image. It allows the user to control the position of the observer here, the inner and outer occulters, as well as a custom field of view, as well as the other options that are available to both approaches, for example, color bar scaling and data transformations. Also, one thing that applies to both the custom view and non-custom view is the ability to select either a brightness image or a polarization brightness image by toggling this switch here. And just to reiterate, be mindful of the relationship between the observer radial distance right here and the field of view. So currently we're considering a plot with a field of view of 0.53 degrees line of sight. But if I was to select a position, say at 1.5 AU, see we'll sort of zoom out, move away from the sun, or we can approach the sun. Let's say I put in 0.5 AU. However, I'm going to simulate a near-Earth observer position and turn this back to 1 AU. Now, with the custom view, you're able to specify bespoke inner occulter and outer occulter. Effectively, what these are doing are masking the values that fall within that domain. Therefore, as one dilates or constricts the occulter, this will have an effect on the scaling of the color bar. This can be particularly helpful in masking extreme values that might crop up close to the photosphere and causes the plot to become washed out. So just to demonstrate this, say I add an inner occulter of 0.2 degrees. You'll see that this solid circle here shows up. You can change the color of the occulter by selecting from the color selector widget here. And let's say I move it a little bit further out, say 0.4 degrees. And for demonstration purposes, let's say I select a different observer position, specifying a longitude of 90 degrees, B angle of 15 degrees, and also a slight rotation with the P angle, say 10 degrees here. And you'll see this orientation axis in the lower left-hand corner of the plot shift along with the actual orientation of the brightness image itself. And now we can move on and take a little bit more of a detailed look at the view widget down here. So I'm going to collapse this. By default, a field of view is supplied. So this sets the x-axis and y-axis symmetrically about the origin or sun center with the provided degrees here. However, if you want to examine a non-regular sort of bespoke view, and it's something that's not immediately apparent, simply delete this value and you'll be provided custom ranges for your x-axis and y-axis. If no value is supplied in any of these fields, we supply a sort of arbitrary default value of 0.53 degrees. So right now that's going to look like a sort of the regular field of view here. If I was to type in 0.53, we get a very similar looking plot. But let's say I wanted to extend the x-axis range to -1 degrees and 1 degrees. Now I'll have a rectangular plot here. There we go. But also if I wanted to examine just this upper right-hand portion of the plot, I could do that by saying, let's say the minimum value for the x-axis is 0.33, and the y-axis we can set to between 0 and 1. Now we're examining sort of more closely just that upper right-hand portion of the original plot. And now, similar to Parker Solar Probe's Whisper 1 and Whisper 2, if you've provided view limits that omit the sun center, you can toggle on this option here, Show Sun Center, and it will extend the X and or Y axis to include the origin. And another really cool functionality of this view widget is that you have the ability to construct wide-angle views for heliospheric brightness or polarization brightness. So let's say starting off with a field of view of 1 degree line of sight. I can extend this quite large up to 90 degrees here, and I'm going to select the heliospheric domain. And I can even extend this out to 180 degrees on the x-axis, but it'll be capped off between -90 and 90 for the y-axis. Also, I'm going to select the MHD vignetting function. Actually, I'm going to select none for that, and then log scale it. We get this really beautiful image of the heliospheric brightness. And with the white light tool, as well as coronagraphs, UV and X-rays, and the UV imager tools, you can download this plot as a FITS file by selecting this Download Data button right here. With that being said, that concludes our overview of the white light tool on Predictive Science's MHDweb 2.0. The next video in this series will go on to explore the coronagraphs tool. Once again, if you have any questions, comments, or concerns, please leave a comment below, and thanks for watching.